magnetic braking with Faraday. The purpose of this lab was to first collect observational data as a magnet falls through a conductive tube of aluminum foil, then to observe the electric field of that bar magnet as it falls. The results from this experiment were that the aluminum tube causes the magnet to fall more slowly than without the tube. Specifically, it took 1.232 seconds experimentally, and then according to the model, it took 1.386 seconds. The physics concepts that were needed to understand this lab are the Biot-Savart law, Faraday's law, and Newton's laws. The Biot-Savart law tells us the magnetic field of a dipole, which is the bar magnet in this case of the experiment. This states that the magnetic magnitude of the magnetic field is equal to mu naught over 4 pi times 1 over the radius cubed, all times 3 times mu dot r hat times r hat minus mu. Faraday's law explains how a change in magnetic flux induces an EMF across a loop, and then when this loop is a conductor, that creates a current throughout the loop. This EMF is equal to the negative derivative of the magnetic flux, which is equal to the negative derivative of the integral of the magnetic field times the area. And using Newton's laws, specifically the momentum principle, we were able to deduce the formulas to update the position and the velocity of the bar magnet. Going through the procedure of this lab, we started by dropping a bar magnet down a tube of aluminum foil, and we timed and recorded the amount of time it took for the magnet to exit the tube. Then we repeated this process 5 times in order to get the average time. Here are the measurements for the experiment. The length of my tube was 0.3 meters. The thickness of the aluminum was 0.01 meters. The inner radius was 0.023 meters. The total radius was 0.033 meters. The mass of the magnet was 0.024 kilograms, and the value for mu, which was found in lab 3, was 3.5 amps per meter squared. On the right side of the screen, you can see the times for each trial of how long it took the magnet to leave the tube, and so you can see that the average time for all 5 trials was 1.232 seconds. Moving on to the computational model for this experiment. For step 1, I initialized the code using the data shown on the last slide. And then this segment of the code is creating a function which calculates the magnetic field of a bar magnet. In order to do this, I used Biot-Savart law, which was shown a couple slides ago. This part of the code is defining a function that finds the time derivative of the magnetic flux, and then this segment shown at the top part of the screen was used to find the current in the ring, and then the segment shown at the bottom half of the screen was used to find the magnetic field at each ring. At the top part of this screen, you can see the code that was used to calculate the gravitational force. In the middle, you can see the code that was used to find the net force, which is just the gravitational force plus the magnetic force. And then at the bottom, you can see the script of code that was used to update the velocity and the position of the bar magnet as it fell. Here are the results from this glow script model. On the left side of the screen, you can see the magnet as it's falling down the tube. And then on the right side of the screen, you can see the graph of velocity versus time. The amount of time that it took the magnet to fall through the tube from the model was 1.386 seconds. To interpret the simulation, the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. I was able to deduce that the red coloring on the ring represented the counterclockwise direction, and the blue coloring represented the clockwise direction. So this is just a combination that would cause the magnet to move more slowly, so it has to be correct. What happens to the dynamic of the system when you flip the magnet around? So if you did this, the magnet would still follow the same slow motion, but the current will flow in the opposite direction with this direction of the magnet. And then how does the total time in tube of your real world system compare to that of the computational system? The real world and the computation systems are different because the real world is more accurate than the model due to the fact that the model does not account for resistance. So adding that to the computational model would make it more accurate. And then finally, what does the shape versus time plot tell you about the forces acting on the bar magnet? At one point in the graph, the velocity is constant, which tells you that the net magnetic force is equal to 0. That tells us that the gravitational force had to cancel out the magnetic force and cause a net force of 0. So what if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? With reduced reduced resistivity, the magnet would fall more slowly, and if the resistivity reached zero, it would stop falling completely because the magnetic force would overrule the gravitational force. And then if there were holes or slits cut into the tube, this would result in the magnet falling faster, and the reduced number of rings would cause the induced current to also be reduced.